Welcome back. Today is February the 11th, and we're going to try to finish mass spec today so that we can review it on Tuesday, and we will have our first milestone, which is milestone 6, on the following Thursday. All right. Now, we're following on this packet, or block, I would say, in this module for our syllabus. And I'm hoping you're having a good experience because mass spec, NMR, infrared, it is the reason, it's basically the reason why our life expectancies are longer. Think about it. Without those techniques, we wouldn't have the medicine we have right now. So it's really, really important. So some students say, what do I need spectroscopy for in life? Dude, this is extending your life and you're having the opportunity to learn about it. How cool is that? Without these techniques, and also polarimetry, I'm going to throw that in there, and crystallography and all that, those other techniques, we would be enjoying the life we have right now, honestly. So that's kind of cool in a way. So let's continue learning about these techniques. So I want to keep you motivated, give you a reason to like this stuff. Okay? All right. So today what I'm going to do is I'm going to go through the 3 types of fragmentations. I'm actually going to manually do it here again and reproduce my work. So let me go to slide 10. There are 3 types of fragmentations, the main ones. And then there's one special one for ketones called where you find the McLafferty ions. So I throw that as a number 4. All right. So if you learn those four fragmentations, plus know the type of patterns the isotopes of chlorine and bromine will give you, the fact that the base ion is the tallest peak in your spectrum, and if you have an odd number for the mass that's equivalent to a compound having a nitrogen, then you know mass spec, basically. The thing, though, you have to figure out how to calculate those fragments, and it could be a little bit challenging. Even for me, I sometimes find the challenge. Last time I couldn't find the baseline base peak on one of the knowns for the mass spec packet. I think it was like a 42, and I don't know what the computer did, honestly, to give us that as a highest peak. I could find 41. That was the closest thing I could get to it, but I couldn't find 42. I was 1 proton short. And but the thing with mass spec, though, it's you don't need to solve for the entire spectrum. That's the coolest thing about it. Like, for example, the benzene ring. So if you have a fragment with a benzene ring, usually that fragment is 77. But then you'll see that if you have a benzene ring, you have all kinds of peaks prior to that. And it's the ring opening and degrading to different fragments. But once we say, oh, I find a fragment at 77, that's all I need to know. I know that, are you Howard? Sidney Howard? So then I say, okay, so that's all I need. All right, so here's it. You're very welcome. I know, right? Oh, I didn't bring the baseball today. Yeah, that was when we had like active shooters in the country. I went to a few seminars and they kind of educated us how to deal with situations like that. Like, that's life or death, man. All right. So let's learn the first 3 more important type of fragmentations. And some of you have already watched my videos and stuff. So this will be a review for you. Okay. And so it's kind of cool to see something twice, honestly, because then you reinforce some ideas. And you learn more. All right. So the first type is when radical cation loses a small neutral molecule like water. So I call this one loss of water. All right. So we're going to do this, and I think we have enough time to do this, and then we'll practice Pack A from my practice homework. Loss of water. All right. So here you have a molecule of water, and most of the time you're going to see that the alcohols, very rarely, some of them keep the molecular mass, but most of the time they do lose a molecule of water, which accounts for 18. It's a mass of 18. 1 oxygen 16, and 2 hydrogens makes it 18. All right. So here we go. So you have this molecule of alcohol. One electron beam is gonna hit that molecule, and so a non-bonding electron is gonna be kicked out. So I'm gonna take this one like that and kick it out. So a non-bonding. Remember that in an energy diagram, the non-bonding electrons will be higher than the pi, and then higher than the sigmas. That will be low. All right. So the non-bondings are the easiest one to knock out first. So a non-bonding electron is ejected. All right. So we will have a CH3, CH2, CH2O radical plus H, and then one lone pair of electrons. All right. One thing about let me see if I'm recording. All right. So we're back. Okay, so we're recording now. So one thing about mass spec is that you have to understand that you have to keep an inventory of electrons. All right. So if you lose one electron, you have to put a plus there. And when we do the breakage, keep in mind that you might form 2 radicals, and those 2 radicals can form a pi bond, for example. All right, so we're doing that. So this will generate the possibility for the beta, one beta a hydrogen to be taken. Check this out. So here's your alcohol molecule. There's a plus here and a radical here, there. And then this is alpha, this is beta, and these 2 hydrogens are also beta hydrogens. So you're gonna go, that's half an arrow, and so here you have 2 electrons, right? One of these electrons come and combines there, and the other one stays there. All right. So for this molecule, the oxygen grabs a hydrogen, and then you form a plus radical or a cation radical. So here you have this. You form a new bond. This is the new bond that you form, and so you have a radical here now. There's a hydrogen there, and these 2 electrons right here forming this bond are going to leave. All right, and so what you will get is you will get this. And so this plus water, this will be seen on the mass spec. This is unseen because it has a full octet. So it will be invisible. But you know that was there because you subtract from the original mass ion to the first fragment, and you will see a loss of 18. So that tells you that you lost water. All right, so water means loss of a mass of 18. All right, so I always tell my students to, if you're in a pickle and you don't remember exactly how this works, there's always a shortcut for those of you who have a powerful memory. So basically, I'm gonna put the shortcut here. All you gotta do is, I'll do this in blue. You're gonna put a plus on the carbon where the hydroxy group was, and you're gonna put a radical on neighbor C. So this is the neighbor C, which is the beta carbon. All right. All right. That's the first type of fragmentation. All right. When we did, why this is the alpha carbon? Well, it's the alpha carbon because it holds the highest functionality. For carbonyls, the alpha carbon is the carbon next to the carbonyl. It's weird. But that's how they started it, and it's stuck with us for, centuries. So this would be alpha, this would be beta, and this would be gamma, for example. So you have to watch out for that. Any other group with functionality other than carbonyls will be the alpha carbon. Like, for example, you have a alkyl bromide. The carbon holding in bromine is the alpha carbon. All right. All right, so the other type, the second type is, and please stop me if you have a question, because I'm assuming you know this, so, but that might not be the case, or there might be a sudden question that you want to ask. So the second type is when we defragment alkanes, and usually we form a cation radical. Okay. So in this case, you will lose an electron from a sigma bond. So this is a loss of a sigma electron. And then here you have, like remember that every sigma bond it's made out of 2 electrons. So, excuse me. So here, you could knock out any of those electrons out, including the CHs also. They're not shown there. Those would be the easiest one to knock out because those are outside the molecules. If a beam of light hits an alkene molecule, it's definitely gonna hit for sure one of those CH because there's more. And they're outside. And so we talked about this last Tuesday. The representation in books for this kind of ions is a plus with a radical outside brackets on the molecule. All right. So let's say, for example, here we've talked about also carbocation stability. So look for the formation of the most stable carbocations. So if this is a carbocation stability ordering, so tertiary will be more stable than secondary, more stable than primary. So for example, in the case that I have, I'll say, okay, I have an impact on A here, or I'm going to represent this impact for B here. What I'm saying is I'm going to break, but I promise you I won't make the breakage sound. Okay. So, we're going to break this molecule like that for A, and for B, we're breaking it kind of like we did it anyways. A little bit, little dab. Right there. All right. And so, when you do this, the fragmentations, we have A. So A, the fragmentation of A will give you what? It will give you, notice that I chose that radical next to the longer chain. So that means I'm gonna put a plus on this carbon right here, right? Because if I knocked out that electron closer to that carbon, that's gonna make it plus. All right, so this is gonna look like 1, 2, 3, 4, 5, and a plus here. And I will also get a radical CH3 group, which is the top. All right, you see that, right? This little point here, this is a CH3 group that is there. But because it's linear, I don't want to even put it in there. I like it linear. So this is not seen on mass spec. All right, and B, if I do the cleavage on B, that's going to produce this carbocation plus, let's see, if I click that, yeah, plus this one right here. And so the one on the left will be seen, but the one on the right will not. This is not seen. Not seen on the mass spec. All right. So this is the formation of cation radicals on alkanes. Also, I call this sometimes a direct hit. All right. So, yes. All right. So I need to speed up a little bit. All right. Let's do the third type. This is the most interesting type. This is the alpha cleavage type. All right. Alpha cleavage. So in the alpha cleavage, you start off making your N plus ion by knocking out a non-bonding electron. So I'm going to do this. Notice that the molecular mass here is 60. So I'm going to hit, this is going to be electron beam minus 1 electron is ejected. I'm always going to pick this guy and then take it out. Bling. So that's going to make this. So you have 1, 2, 3 carbons, 3 carbons and an oxygen and an H. We have this. All right. So here is the thing that is new. This is an alcohol. So the alcohol can undergo two things. The alcohol, and that's why I got confused last time. So the alcohol could do the loss of water, which is a type of fragmentation, but it can also do alpha cleavage. And so this is the alpha cleavage. Once for alcohol, this is how it works. And remember that what we're trying to do here, explaining how we get this fragmentation. So for the alpha cleavage, you're going to cleave that bond in half. So I'm going to use black. So this one will come here and this one will go there. And check this out. So this is the alpha, this is beta, and this is gamma, right? So that means between alpha and beta, that is your alpha bond. So this is this one. This one, hold on, okay. This one is your alpha bond. Like this one will be your beta bond. All right. All right. Okay, so when you do this cleavage, it's homolytically. And so you will make, so I'm going to put here alpha cleavage. Can we see that? Yeah. So we do the alpha cleavage. What are you getting? So you're getting this ethyl radical plus this OH, it's actually a biradical. You have one here and one here. You see that? And then when two electrons that are unpaired are in proximity, they would like to merge and make a pi bond. So we're going to be making a pi bond with this oxygen. Now keep your inventory. You start with 3 electrons and a plus. Now you made a double bond. So you're left with a plus, a hydrogen attached to it, and 1 pair of electrons. You see that? And so this has a full octet, and it can be seen on mass spec. All right, awesome. Let's do the alkene one. So this was a non-bonding experience, knocking out. Now this other one, this one is going to be a pi electron being ejected on this other one. So we're going to do that. So here we have an alkene, and we have 1 lone pair here. I mean, 2 electrons here. It's not a lone pair, sorry. 2 electrons. And so here is my blast of electron beams. That's going to, I'm going to take that one and kick it. All right. So we're going to be losing 1 pi electron. So this is loss of a pi electron. And then you make this. Check this out. So you have now a radical here and a plus on this carbon, because this carbon is missing an electron, right? The other one was your sigma bond, still there. This is your sigma bond. You're still there here. All right. So you haven't lost that. All right. And so check this out. They call this the alpha bond. And that baffles me. Because I don't know why. Because, let's see. I guess is the carbon. I guess this is how the way I see it. The carbon holding the functionality. This carbon right here is holding the functionality of the radical. And I guess that's the only thing that I can think of. This one is hard to explain, honestly. But that, they call that the alpha bond. All right. So you're going to do the same thing here for the alpha bond. So what is the alpha bond? The alpha bond in this case is the bond with the carbon that is next to the radical. All right. Yes.
Dr. Knight, when I took OCHEM I, he said that alpha bond was the bond between the alpha and the beta carbon.
Yes.
And like that's just how I would remember it.
I know that. The problem is how do they pick this as the alpha? See what I'm saying?
Oh,
You see what I'm saying? Yeah.
because I was confused too. Like
Yeah.
on the online notes,
Mm-hmm.
I had that question too, but then I was just like, I just keep remembering the alpha bond is like the one between alpha and the beta.
Yes.
I won't ever get confused because I didn't know I.
Yeah. Like for example, here we say that the alpha bond here is the one between the alpha and the beta. That's right. But the question I have is, why did they pick this carbon to be more important than, for example, the one with a plus? Or, you know, it baffled me. That's what I was trying to say. But you are right. You are right.
Is one more stable than the other? Like the carbocation, is that one less stable than the non-positively charged one?
Possible. And the fact that it has one extra electron, that makes it more important, I guess. But why not? And then why not calling this the carbon that is alpha? Because it has the functionality. You see? So I don't want to get you confused. The only thing I know is they call this the alpha bond. You see what I'm saying? You see my predicament? I cannot explain this. But the people call that the alpha carbon, the alpha bond. Meaning this must be your alpha carbon, and then this must be your beta, because you're right. It's the alpha bond is between the alpha and the beta carbon. All right. So this is gonna cleave. And it does that and that. And I guess this is one of the times in OCHEM where you had to like use your memory, basically. And I hate using memory. So this would be not seeing on mass spec. And so what do you get? Do you get look what you get. You get this thing here, radical here and a radical here, and that does that, and so you get an allylic. Allylic carbocation. All right. Any questions up to this point? I think we have time for. Oh no, let's do this next page. This next page is awesome. All right. All right. So let's talk about alpha cleavage of aldehydes and ketones. So here we go. So the alpha cleavage just happens to, it just breaks in half. It's homolytically. So you have this, you have that. You can do alpha cleavage here or here. For this molecule of aldehyde, you can do it on the right or on the left. Right or left. All right. And so here are the different options that we have. Let's say, because this ketone here is symmetrical, so either one is the same. So I'm just going to erase the one on the left side. So symmetrical, you only have one option. So here you have one option. One option. For this one, you have two options. And for this one, you have two options. All right. And so here we go. So option number one for the top, and the only one there is, so pretend you already have knocked out your non-bonding electrons. So these fragments will all come from the N+ ion, okay? So we're dealing with the N+ ion all the way here in all these examples. So let me change pens. So here we will have, so if I break this, one will go that way, the other one the other way. So we will get this. And this fragment is, at this point, is trigonal planar It's got 3 directions. So you go, and then you turn that into a resonance, but you need to show it as the right geometry, which will be linear. Because now you made another bond, this guy, that's a new bond. You make a triple bond O, then carbon, carbon. So this is what is called an acyl cation. And it has a full octet. All right. All right. So let's take a look at the next example, the aldehyde. The aldehyde has 2 options. You can make the acyl cation, and you can make the acyl cation with a hydrogen attached. All right. So basically you will. So let's call this option option A. I'm gonna break this in half. So you will make and also you could also get the same fragment if you do a direct hit. If you do a direct hit there, you'll get it. All right. But we're looking at the homolytic cleavage. That will give us that. This will be A. This is your acyl cation. And B will be this guy. The O plus with 2 electrons and a triple bond with an H. This will be the B option. All right. So basically, for an aldehyde, you will see that you have your N plus in this case. Yeah, I think we saw this example in lab. You have 58, and then you have a 57 ion. So this is loss of hydrogen. All right. All right. So there's only a difference of 1 there. All right, and then the last example gives us 2 different acyl cations. Check this out. So let me work this out. So you have option A here, and option B right here. Again, you can do this by doing that, or by a direct hit here. Also, you'll get the same result. This one will give you this guy. So I'm gonna do this in process. So we'll give you this. Again, I'm gonna repeat the first one, like the first example. And these 2 electrons will merge to make a triple bond. So you make this plus and a lone pair with an ethyl group hanging on. And then the other option will be, if you do B, so this will be A, so this will be A plus O, H, and then have a lone pair like that. And now here you will have the other option. So this is option A, and option B will be an oxygen with a lone pair and a plus and a triple bond attached to an OH, and this would be B. Plus, what would you have here? An ethyl radical. All right, not bad. We got 30 minutes, about 30 minutes. No, 26 minutes. Let's work on the first packet. All right. Let's work on the first packet. All right. That's all. Oh, I forgot the McLafferty. Sorry. Let's do the McLafferty real quick. Here's the McLafferty. For the McLafferty, let's go to slide 23. I don't want to leave the McLafferty out. All right, so here's the McLafferty. Here you have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this is 4-methyl pentan 2-on. So this is a ketone, and notice that the McLafferty will produce the following ion. Hold on, let me see something. I need to see something here. Oh yeah, I have found it. Oh, by the way, I put the key on the quiz for the NMR. It's on Canvas now. Yeah. Let's see. Okay. I think I got it. Why is it different? Oh, I got it. All right. So check this out. So this is how you get the McLafferty ion. So basically, this involves a 6-atom ring. So you're going to form like a rearrangement among 6 atoms. 1 oxygen, 1, 2, 3, 4 carbons, and 1 hydrogen. All right, you're going to arrange it so that it looks like a 6-member ring. All right, so it's already the N+ form. So this is the N+ form of the molecular ion, and you're going to do the following things. So notice that here you have electrons all over the places on this sigma bonds, right? You have that. Actually, I'm not gonna draw those. I'm gonna draw the ones of interest. This and these two. So you will have 2 sigma bonds involved and 1 pi bond involved. So here we go. So this is how it starts. The oxygen is the most electronegative of all the atoms here, so it's gonna get started. It's gonna steal this hydrogen. So basically, you're going to be forming a bond there with that move. That move means you're forming a bond there, all right, a sigma bond. Now, this one is going to break and form what? That's going to form a pi bond. And here's the cleavage here. So for this one, for this case, this is going to do that. And this electron also is going to help. It's going to help this electron to get an actual minus charge to grab that H. All right? All of that forms this. That forms an enol. This is an enol cation radical. All right? You see the enol? So here's the ene part, the double bond. And then the OH is your ol, so enol. All right. So this is how it's easier to spot it. This is actually the most abundant form of this ion, but the book shows it like this. So the book actually wants to trick us a little bit and saying, okay, you know, the keto form is more stable. Okay, fine. So it'll be, this is the keto form. So you're going to rearrange this. You're going to put a radical here. The pi bond will be there, and then you put a lone pair with a plus and an H. This is the keto form. Either form that you show it to me on a quiz or exam will be fine. So this is from our notes, and this is from the book. How cool is that? You see that? All right. So now, any questions? I think I'm done with the 4 types of radicals. Any questions? No? All right. Let's go to the next thing that we're going to be doing here. Let me say this as in class. Oh, it's already in class. Good. That's loud. Sorry. That's how it would sound if I played the piano. Yeah. Bang. All right. I'm going to get out of here and find the pack. The pack for the winter pack check on. Yeah. All right, so I'm gonna do the mass spec pack A. There's no way to save as. Sorry about that. That is annoying. At least that wakes you up, right? You should be awake. It's 10:20. All right. I'm going to try to finish this in 15 minutes to give 5 minutes to like exchange your homework with me. All right. So here we go. I'm going to follow the advice of Hunter and use my PDF directly. That's awesome. All right. So all of your packets have this. Not that line, but hold on. Have this initial blanks pages. So basically, the idea is that you fill this out. Let's do that real quick. All right. So you have acetamide. Acetamide means 2 carbons. That's common name. It'll look like this. Wait, let me do it properly so you can see it. So the molecular weight is C2H5NO. So if you don't have the molecular mass, you can always calculate it, and you'll have a mass periodic table of elements available in the exam. So this would be 59. Acetone, super duper easy. This is C3H6O, and the mass is 58. Then we have 1-butanamine, and one more, C4H11N, and that has a mass of 73 because it has a nitrogen. It'll be an odd number. Butane is the mark of Zorro, right? So this would be C4H10 and has a mass of 58. So that's why I told you only do this once, and then just work on the mass specs. Butanol, 4 carbons and an OH, and so that will be C4, and then it has 10 hydrogens and 1 oxygen. 1 oxygen, and the mass will be 74. 2-butanone is this, C4H8O. So this used to be a lab that I used to give to my students, a dry lab, just like what you do over here. But I will start off with this, so that student will have to calculate the molecular masses. And I'm going to show you why. Because this is more fun. C4H6O, and then this is 70. Chloroethane is a double bond with a Cl. C2H6Cl. So here you have an option of saying, okay, this would be 62 if it is the Cl35, right? or if it's Cl37, it'll be 64. All right. So we keep going. I'm gonna leave that there. Ethyl chloride looks like this, and this is C2H5Cl, and so 30. We're using 35, so it'll be 64. Then we have 2-methyl 1-butanamine. So butanamine is this, and 2-methyl will be that. So this will be C5H13N, and then this is a mass of 87. Let's see. Again, what we're doing here is we're using, let's put that in here. We're using carbon will be 12, as you know. Hydrogen will be 1. Let's see. Carbon will be 12, hydrogen will be 1, oxygen 16, nitrogen 14. Sometimes I get confused with nitrogen, but it's 14. Cl is 35. Cl could be 35, or Cl could be also 37, and then Br could be 79. Use 79, even though it says 79.9, use 79, okay? Because the isotopes are 79 or Br 81. Those two. All right. Just like for chlorine, just use 35 instead of 35.5, which is what you see on the periodic table. That will simplify things, and that's what the mass spec will actually read. All right, so we're finishing up this. 2,2-dimethyl-1-propanol is like this. This is a cool molecule. All these molecules are in your packets. I think all of them. And this one, 2-methyl. Check this out. 2-methyl, 2-propanamine is that. This is C4H11N. That's an 85. That's another odd. We find another odd here. That tells you immediately that you're dealing with a nitrogen. 1-propanamine. This is also going to be odd. C3H9N. That's a 73. This is odd. So if you have 73 there and a 73 here, those two will be competing. The next time you see an N plus that has a 73, right? So then you have to, that's why it's more fun. That's why you have to then figure out which one of the two it is. Propanoic acid for 3 carbons, carbonyl group C3H6O2. This is 74. 2-propinal. So it's an aldehyde with a propene group. It has 3 carbons and an ene. So this will be C3H4O, and it's 56. 2-propenamide will be similar to that, but it will have an amine here. And this is C3H5O, 71. 2-propene nitrile will be this, and we'll have C3H3N, 53. I'm going to speed up a little bit. Propanoic acid, propanoic acid is that. C3H4O2 and 72, and this one is 2-propyne-1-O. So triple bond, it looks like that with an oxygen alcohol. C3 H4O, and this has a mass of 56. All right, so let's do the first one. So here's what you will identify the name of the unknown, and you will find 3 fragments. All right, let's do this. Let's do the first one. Okay, so my options are 2. Let me rotate this. I have 2 options here. Option number 1. So I look for my. So it says 74. So this is my n plus 1. Well, I'm sorry, my n plus. From 72, which ones do we see that we have? 72 are 2 butanol and 2 propanoic acid. So I'm gonna draw those 2. Oh no, this is 74, not 72. 74 will be 1 butanol. So my options are 1 butanol, and 74, the other one 74 is, oh yeah, this one. Those are my 2 options. I'm going to write that option here. This is called 2-methyl 2-propan 2-methyl 1-propanol. 1-propanol. All right. So those are my 2 options. All right. Check this out. How much is 74 minus 56? 74 minus 56. How much is it? 18. 18, right? So it's lots of water. So over here you have loss of 18 is loss of water. All right, so I don't know which one of those 2 is, but do you think, and this is how I throw this, I realized that it's the one on the right, a mass of 43. What is a mass of 43? A propyl fraction, a propyl fragment, right? 3 carbons and 7 hydrogen. 7 plus 36 is 43. So you know that it cannot be this fragment cannot produce. That molecule cannot produce a propyl group. That's how I cancel it. This fragment can only produce methyl groups, 15s. All right. So I'm dealing with butanol. So the first thing I'm gonna do, I'm gonna take butanol, and I'm gonna apply an electron beam, and I'm gonna knock one of these electrons out. I'm gonna knock that one out, and so I'm ending up with a plus here and a radical and a lone pair. All right. So this guy can then do. Let me see. Let me fix this molecule in a way so that it can see it better. 1, 2, 3, 4. Like this is better because I'm going to withdraw this beta hydrogen. So, but this is my molecular ion. So this is gonna be this guy. OH with a mass to charge ratio of 74. All right. Then I can do the loss of water right here, and so this will produce this. Plus 1 lone pair, 1 radical here, and I have 2 electrons that are here that I'm going to take off. So I'm going to do loss of water. I'll have this cool looking radical. This is 56. How many 56? So I have 4 carbons, 4 times 12, 48. And I have how many hydrogens? I have 3 here, 2 here, 1 here, and 2 here. So I have 3, 2, 5, 6, 7, 8. 48 plus 8 is 56. Make sense? So this has a mass to charge ratio of 56. All right. So I'm not done yet. I know that 43. How do I get 43? I get 43 from a direct hit. Let's say, check this out. I get a direct hit here. If I get a direct hit right there, and that kicks that one out, always work from the N plus. So this is your N plus. Then I'm going to make this plus this this radical. This is actually a good one. Here you can have the two fragments that you need. So this will be 43. I mean 43. No, that one. Sorry. 43 is right here. And which one will be? So this will be a mass to charge ratio of 43. And this one will be how much? Notice that you can do this. Now you have a double bond oxygen with a plus, one lone pair, and an H. And so here you have 3 hydrogens because there's 2 here. So you have 3 hydrogens, 1 oxygen, 1 carbon. So that's 3 plus 12 plus 16. 31. Do you see a fragment of 31? Right here. So label that. So this will be H. That's that fragment at 31. I think I can find 41 too. Check it out. Check this out. This is how you find. This is how you find 41. You can find 41. Let me find another pen color. You'll find it by taking this guy and do an alpha cleavage. Alpha cleavage gives you this. And then these two will merge and you make this beautiful thing. This one is that. All right, so we have plenty of ions here. So identity, this is 1-butanol. 1-butanol fragment 1 is my N plus, which is 74. Let's say 74 is my N plus. This is this guy. And fragment 2 will be 56. Is this guy. Fragment 3, I'm going to pick 43, which is my propyl group. And I'm going to put 41. 41 is this guy. And you can put 31 too if you want. So I gave you 5 fragments for this molecule. All right, I don't think I'll have time for the next 2, but what I will do is I'm going to work on them, record them, and send it to you as a video, okay? So that you have a chance to complete this packet and then do the other ones. Have a wonderful day. Please, as you're walking out, turn in your homework. Thank you. I'm sorry? I don't know if there's one here. We have staples, but not stapler. Yeah, I'm sorry, I don't have. Just fold it, I guess. Thank you, guys. Thank you.
Is it okay if I stapled them individually but not all together? But
Oh,
my
yeah.
name's on it.
Awesome,
I did
awesome.
the same thing.
That's perfect. Just put them like that.
Oh, okay.
Thank you. Thank you very much.
I know you have office hours today, but I can't come because I have class. Can we make a meeting for tomorrow? Can I email
Tomorrow I
you?
don't work here.
Oh, okay.
Yeah, I'm sorry. I only be here for office hours Mondays and Thursdays.
Okay.
Do they work on Monday for you?
Maybe. It might have to be over Zoom because I work on Monday.
I cannot do Zoom because I have students coming in and out.
Oh, okay.
Yeah, it had to be in person.
Okay,
Yeah, I have it from 9 until 2 p.m. So try to find me, okay?
Thanks.
And argue
Yes,
as usual.
yes.
Okay, so don't you just like set up for like getting this? Cause I know I got that, but it literally just makes no sense that I ran out of time.
Oh, check my key first, and then you come and argue with me.
No, I know that's wrong.
Yeah.
Like I know that's wrong, but I'm
You're looking like after the arrow, going after the arrow.
Yeah.
I gave you credit for after the arrow here, but those were too off. I couldn't. And this one, I mean, if you had this, why you didn't put that here? I mean, instead of like here, like you have an isopropyl group here.
Yeah.
You identify here, but you couldn't put it together.
You want it like folded in half or just?
No, just like that.
Do you want me to bring this in office hours when I come in there so we can look over?
Yeah. Thank you. Thank you. Thank you. Thank you.
Most of them except I didn't understand 90.
Okay, I understand. You're good. You're good student. So. Okay, let's come out of here. 10:40. It's time to go home.
Thank you, Dr.
You're welcome. Have a wonderful day.